In section 5.4, we're looking at dividing monomials. This is talking about more rules of exponents, more laws of exponents. So we'll first consider this case. If we do y to the fifth over y cubed, well, I know that this is y times y times y times y. There's 5 copies of the y up there and 3 copies of the y down there. Since this is all multiplication, I can cancel factors. I can cancel a factor of y, a second factor of y, and a third factor of y. You can see I was able to entirely cancel out all the y's on the bottom. And since there were 5 up top and I canceled 3 of them, I'm left with 2. I'm left with y squared. In general, if we had a times a times a, if we had a bunch of a's up top, there's r of them up here, and we had a bunch of a's down below, there's s of them down here, then if I was to cancel all of these out, let's assume for now that s is smaller than a, or s is smaller than r rather. If I was to cancel all of those out, I would get rid of all the s's on the bottom, and I would start with r up top, canceling out s of them. I would be left with r minus s up top. And so that's what we're gonna, that's what the first law of exponents is for this section. So here, let's see, if I just use the law of exponents here, 5 minus 3 is 2, so this should be 6 squared, which is 36. Now, it seems kind of silly to use a law of exponents on this particular problem, since those we can just follow the order of operations. Let's see what happens if we just follow the order of operations. We get 6 to the fifth. It better be the same number. And we have 6 cubed. So we have 7,776 divided by 216. And if I actually do that division, I get 36, as I expected. So this is our law of exponents. Again, I'd like to do these with integers like this, or just with general numbers, known numbers, just to verify that things work out. But the real reason we learn these rules is so we can do these with variables. So if we've n to the sixth over n cubed, or n squared rather, well, 6 minus 2 is 4, so this is n to the fourth. If there are other coefficients around, that doesn't really bother me at all, but it doesn't really impact what's going on with my variables. B to the ninth over b to the sixth, well, 9 minus 6 is 3. But then I also have to pay attention to what's going on with my my coefficients as well. There is a common factor of 5 that can be canceled here, and when I cancel a factor of 5, I'm left with a 5 up top and a 3 down below, because this is 5 times 5, this is 5 times 3, so I'm left with a 5 and a 3. I could either write that as 5/3 b cubed or 5b cubed over 3. I'm more of a fan of writing it like this, because this emphasizes the fact that 5/3 is the coefficient and b cubed is the term that's left, or is the variable part. This one is a question mark. I think I wrote this wrong. I think this is supposed to be negative 24 x, let's do the sixth, over 10 x to the fourth times y. So I just typed it in incorrectly there. Alright, if we do this, actually, I think there was supposed to be a y up top also. I don't remember. But we'll do this. Okay, so when you're approaching something like this, you'll notice each part, you can kind of consider these separate. Before, on this previous problem, I was kind of thinking of this as 25 over 15 times b to the ninth over b to the sixth. And that's why I was able to apply this this property of this law of exponents here with the b's, and then I was able to reduce it separately. So that's what I'm going to do here. I'm going to think of the negative 24 over 10 as its own fraction, if you will. So it's going to be negative, because I have a negative divided by a positive, and there's a factor of 2 I can cancel, so I'm going to get 12 over 5. Next, I'll look at the x's. I have x to the sixth over x to the fourth. 6 minus 4 is 2, so this will be x squared. And I have y cubed over y. Well, this is, the exponent here is 3, and the exponent here is 1, so I end up with y squared. So I end up with negative 12 fifths x squared y squared.